Hello, this is Ted Baldery. I'm with EasyPower, and Jim is out today. He isn't available, and he asked me to host this presentation or this webinar. Yvonne Grobelar from Dane in South Africa is going to be doing the presentation today. The way we organized this today was we pre-recorded it, which we do sometimes. And one of the advantages is that Yvonne will be able to answer questions live. So if you look in your GoToWebinar control panel under the questions section, you can submit questions there and he can answer them. Yvonne will also come on at the end of the presentation and be able to, and he'll verbally do some question and answer at the end. He'll mainly just be answering the questions that are submitted through the questions window. We'll go ahead and get started with the presentation.
Okay, hi everyone, welcome. And thanks so much for joining. We're very glad to see that you have an interest in the topic in terms of lighting protection for PV plants. This is something that we work in quite a lot. So my name is Ivan Grobelar. I'm the senior engineer at Dane Africa, which is the South African subsidiary. And one of our biggest project bases are PV. So we do a lot of projects in terms of PV and the light protection for PV plants. And it's a very relevant topic at the moment with the whole world moving towards renewable energy. So what I hope that you take away from this presentation today is an insight on how to incorporate planning for lighting protection into your complete PV plant design. Because this is often neglected, and it's extremely important to get this right from the beginning as it works from the earthing system or the grounding system on the way up. Okay, so just a quick agenda of what we'll cover in this presentation. So first, I would like to show some examples of lightning damage that we've collected over the years to show the relevance of lightning protection for PV plants. And then just to touch base again on the difference between a direct lightning strike and a surge. In the previous presentation we did on lightning protection for grounding systems, we also spoke about this, but we didn't speak about the nearby strike. So I think it's important to also go through this. And then it's also important to understand the different types of standards we use for PV. So the presentation is mainly based on IEC standards, but it's very similar for other standards across the world, and most people have adopted the IEC standards in their national and local standards. And then lastly, we will go through some examples of simulations that we did over the years to do fault finding and to show the importance of lighting protection using the XGS Lab software. So firstly, looking at some examples of lightning damage in PV plants. As I said, this is something that's very common. And there's probably a lot more data that we could have shown than we are showing. But it's important to take away the reasons why these specific damages actually occurred. If you look at the first one, this was a lightning strike that terminated onto a PV module. Okay, so on the left, you can see the front end or the top end of the PV module or the PV panel. And on the right, you can see the bottom portion of it. Okay, so this is actually considered minor damage to a PV module. We've seen much worse. We've seen holes straight through the panel and a lot more glass cracking and things like that. And we will explain how to protect this or to prevent this and protect against it. And also what happened after this module going further down to the electrical system. So that's one of the aims of the presentation today. This is an example of damage to an inverter. PV inverter. So this was a direct strike where energy entered the inverter, and you can see the holes through the PCB and damage and burning to all the electrical equipment inside the inverter as well. Here we can see an example of inverters which were installed in a basement. And after lightning actually struck the PV plant and the system got electrical damage, further subsequent damage downstream occurred. So what happens is when lightning strikes the system or the module, it's not necessarily that you'll only replace that module. there's definitely damage to the DC system or the electrical system, and this can cause DC arcing or any arcing further downstream. This then causes a fire. Okay, so subsequent damage is complete fire to the building, and we have been involved on investigations for insurance companies where this was actually the cause of damage. It wasn't the actual direct strike that caused the fire, it was the subsequent damage after the direct strike that actually caused DC arcing and fire within the system. Here is from a study done in South Africa as well. So this study was done by another third party for TEN or with TEN as well. And in this case, we investigated lightning strikes into the PV system, and you can see DC arcing going through the cable insulation. So it actually arcs and flashes into the DC cabling, causing damage to the DC system. What we also sometimes see is underground cables will also experience that ground potential rise that you would get from the direct lightning current or lightning current entering the grounding system. And that ground potential rise then causes a voltage difference between the surrounding soil and the cable, and it actually flashes over into the cable, also breaks down the insulation. This not only causes electrical damage to the system, but subsequent damage can occur in terms of insulation breakdown that can cause nuisance tripping of circuit breakers within the system. So it will be very difficult to find this type of damage in trenches and things where this cable has been installed. Now, statistics from a German insurance company show that in this case it was in 2017, the ratio of damage to PV plants and what actually caused this damage. So you can see the biggest portion of this damage was due to lightning. It was about 42%. So this makes this a very, very relevant topic to understand and investigate, and to make sure that you plan for this through the process of design and construction of your PV plant. Now, to understand why lightning causes damage to the PV plant and what different ways lightning can cause damage, we need to investigate the difference between something like a direct lightning current and a surge current. Now, the standard IEC 62305 and part 2 of that standard is all about risk assessment. So what we do in the standard is we calculate the probability of your PV plant getting struck, or any structure for that matter getting struck. And based on that, we would then do a financial calculation to see what would the cost implication be for installing lightning protection versus just paying out the damages. And we also check the implication of human life hazards for lightning strikes. Unfortunately, with something like in a PV plant, which is a very open area, there's no real way to protect people within the PV area from direct lightning strikes. People in the outside zones or in outer areas cannot be protected by lightning or against lightning. But what we then do is we incorporate evacuation techniques and evacuation systems to evacuate people with early detection systems and get them out of the plant when a lightning storm comes in. So we mainly then focus on the economic risk for PV plants to protect the actual asset. Okay, so to do this calculation and to understand, there are two different collection areas that we calculate. So we call it collection area, and that's the area where lightning can strike directly into the plant. Okay, so if you look at this picture on the left, this is referenced from the DEN lightning protection guide, but it's just the same picture that you would find in IEC 62305. So what we do is we calculate the area for direct lightning strikes, and this is called AD, the collection area for direct lightning strikes. And we would take 3 times the height of the PV plant or the structure that we try to protect, and we draw a radius for that value around the PV plant. Okay, so that's the area in which we can have direct lightning strikes. We also then check how many nearby lightning strikes we can have. So a nearby lightning strike is also referred to as a surge. This is when lightning strikes somewhere within the vicinity up to 500 meters away. So if you take a radius of 500 meters away around the structure or the PV plant, Any strikes within this area is considered a nearby strike. And what happens is when lightning comes down, it strikes from cloud to ground, it creates this massive magnetic field, and that induces a current again in all the conductive parts inside the PV plant. And that causes surge damage. So that causes damage to the electrical equipment. So when we do these calculations, one of the biggest things we calculate are these two areas called collection areas. So it's AD for the collection area for direct strikes, and AM, which is the collection area for nearby strikes. Now on the right, I have an example of one of these calculations. So in this case, we drew the PV plant in a risk calculation software, and you can see the dotted lines around the structure. So that makes up the direct strike areas, and then you can see the values there. Okay, so the value is huge for nearby lightning strikes within a PV plant. So you would typically see a lot of surge damage around PV plants and a smaller portion for direct strikes, as the collection area calculation is shown to have a smaller collection area. But what you can take away from this is PV plants have a large collection area, as opposed to something like a substation or a building or a hospital, anything like that for that matter. And due to these PV plants having a very large collection area, lightning will affect it much more often as opposed to a building. So in lightning, we talk about the lightning ground flash density. So that's the factor of how many times lightning will strike per square kilometer per year. And even if the value is 1, so let's say we had a flash density value of 1 lightning strike per square kilometer per year. If I have a small building that fits into that square kilometer, the building might get struck once every 10 years, once every 15 years. But PV plants take up a much larger area, so the chances grow. Even if the lightning flash density is 1 and the PV plant takes up 2 square kilometers, means it can get struck up to twice a year. So for that reason, it's very relevant to really consider lightning detection for PV plants, purely because of the large land mass and the large collection area that they take up. From the previous presentation, we also touched base on this. The direct lightning current and the surge current are defined by 2 different wave shapes. Okay? This is due to different amounts of energy. If we talk about a direct lightning strike into a PV plant, we call this the 10 by 350 microsecond wave shape. For a surge or a nearby lightning strike up to 500 meters from the structure, the value is known as the 8 by 20 microsecond wave shape. Okay. So in this graph, we show both wave shapes, which peak at 40 kiloamps. Okay, so the red graph is the 10 by 350 microsecond wave shape or direct lightning current wave shape. And what happens here and what it means is that it will reach its peak value, in this case 40 Ka. It will reach it in 10 microseconds. Okay, so we use the 10 microseconds, and it will decay to half of its value, which is 20 Ka, in 350 microseconds. That's what the wave shape means for direct lightning current. For surges, it's similar. It will reach its peak value in 8 microseconds and decay to half of its value in 20 microseconds. So obviously, you can see that there's a big difference in terms of the area under the curve. This area is also known as the charge of lightning current, which we'll explain a bit later in the presentation as well. What you can take away from this, the charge and also the energy with something like a direct lightning strike is much more than that of a surge. So we protect against these in 2 different ways. The one in the red curve will also happen less often in something like the green curve. So we will have more direct lightning strikes. We would have more surges than direct lightning strikes, as you saw in the collection area calculation on the previous slide. To show the effect of surge and how it quickly changes the further and further way that it actually strikes, we did these studies in Germany at our test facility at our headquarters. And this is just to give you an example. If you had a PV module, for example, that was installed half a meter away from a lightning carrying conductor, we inject 50 Ka in this case in the lightning carrying conductor, and then we measure the induced surge current in the module itself, and we move the distance away to show you the difference. And this is what we saw. So if you look at the curve on the bottom, here we actually have the current that we inject in the conductor, which is 50 Ka, 10 by 350, or direct lightning current. As you can see, with the distance at half a meter, we measure about 1 kA of induced current inside the PV module. As we start moving this away, for example, to 1 meter, it's half a kA of induced surge current that's induced in the module. So this is very relevant also in how we route conductors and things like that within our PV plant. If we have a lightning carrying conductor that's running very close to electrical cable, this is definitely relevant. You would start seeing this induced current inside your electrical system. Now, to understand how we would mitigate against these different risks and these different types of direct strikes and surges, we need to go into standards level to understand what the standards say we need to do to mitigate this. There are two main standards that we use for lightning protection in PV plants, which is the IEC 61643-32, and also the main lightning protection standard, which is IEC 62305, and it's made up of 4 parts. If we go into IEC 61643 part 32 first, there's an annexure A at the back of the standard that clearly highlights the mitigation techniques for a free field or utility scale PV plant. Okay, so the first thing that we take away is the standard says you need to install a grounding grid across the entire PV plant with 20 by 20 meters of mesh material. So it would be something like copper or galvanized steel that forms a mesh under the plant of 20 meters by 20 meters. And then the standard just says that for larger scale plants, you can go to 40 meter by 40 meter. Now, this value is extremely important for how the lightning protection system will operate. It's something that we managed to change and adapt quite a bit by using simulation software to not strictly adhere to a 40 meter by 40 meter mesh, but to form some form of meshing that's mixed between above ground and underground material. Now, this value is extremely important for what you will see throughout the rest of the presentation. Okay, so the meshes are there that stress is reduced on surge protective devices, so SPDs is surge protective devices, and other equipment within the plant. So all that means is that if there's a lightning strike in this area, for example, the current will split through a bunch of meshes of earthing by the time it gets to electrical equipment. So the energy has been dissipated and attenuated quite a lot, and we don't overstress the surge protective devices that protect the equipment. And what the standard also says is that it's recommended to install a lightning protection system with finials and masts of a lightning protection level 3. Okay, so this is only a recommendation. And what this means is that if you remember from the lightning protection standard, so a lightning protection level 3 means that we will have a lightning strike of 100 kiloamps. Okay, and what the standard then says is that the surge protective devices installed at all these green boxes only have to withstand a total of 10 kiloamps of lightning current for varistor type surge arresters, or 20 Ka for spar gap based surge arresters. So you can see firstly, we inject 100 Ka of lightning current. But if a surge arrestor only complies to 10 or 20 Ka, it's deemed compliant. And this is purely based on the fact that the current splits to this meshing system. That's a requirement from the standard. So it will be much less by the time it reaches equipment. The standard also says that if the soil resistivity becomes higher, the current will not split as much to the earthing system and might follow above ground routes, and it can further overstress surge arresters. Also, if the meshing is not enough, it will affect this and more current will flow through the DC system. Now, what a lightning protection system would typically look like is for a PV plant in this case. You can see this is a side view from a tracking system with a PV module on top, and we have a finial or lightning air-termination rod installed on that. Okay, so that's the first one, is the air-termination rod. Secondly, when lightning strikes this air-termination rod, it has to make its way to the grounding system via the pile or the pillar of the PV tracking system. To do this, they are usually insulated by a plastic bearing. So we have a specific conductor that we will bridge across that. So lightning current goes from that arm into the pile down into the grounding system. And ultimately then it distributes through the earthing or the grounding system. and the energy is dissipated. Okay, so the placement of these rods are calculated with the rolling sphere method, as you can see in this case, where we use the rolling sphere method to see how many air-termination rods we need to install and where they need to be. Okay, so ultimately, lightning will strike the air-termination rod. The lightning current will flow through the air-termination conductor down to the tracking arm via a cable through to the arm, the pile, and then down to the meshed earthing system. Now, that's the background of direct lightning strikes, surges, and how we protect against that. Now I will show you some case studies that we performed using the XGS Lab software and what we saw during investigation if we take some of these components out of the equation. Okay, so the first one was where we didn't have air-termination rods installed. We took that out of the equation and then checked what would happen if lightning strikes the PV module directly. Would we just replace that PV module, or would there be more subsequent damage further downstream? Okay, there's a big misconception in the market that people would only replace the module and everything is fine, and that's much cheaper than installing something like grounding and a lightning protection system, which is not the case. In the second case study, we will look at poor current distribution through the grounding system, where the grounding system was neglected and other subsequent damage occurred. Things like fuses and circuit breakers within the PV system also actually got damaged due to this. Okay. So when we jump into the first case, as I said, in this case, we remove air termination from the equation. So the first issue would be a direct lightning strike onto a PV module and to see what happens to the electrical system further downstream. So this is our setup. In this case, we use the XGS Lab XGS time domain module. As explained previously as well, when we perform lightning current simulations, we need to perform this in the time domain using an impulse wave shape. Okay. So there were two things that we investigated. The first one, we wanted to measure what happens within the system if we strike lightning directly onto a PV module. So we don't have the dedicated path of air termination to the pile and into the earthing system. That dedicated path was removed and it strikes the module and it has to find its own way down to the grounding system via other metallic structures and arcing and flashing and things like that. And the second one, we will show how if we install an air termination rod and we give that dedicated path, how the stress on equipment is suddenly removed and how the subsequent damage further downstream in the DC system can actually be avoided. As I mentioned, in the XGS time domain module, we need to simulate with a time domain or impulse. And in this case, we would use a lightning level 3 impulse. As you can see there, this is, as we said, from the standard, we generally would protect against up to level 3 for free field PV plants, which was a recommendation from the standard. So we would use this specific wave shape, and we will see how this propagates and moves throughout the system. So again, we have our rise time up to 90%. In this case, it would be in 19 microseconds for simulation reasons, and it would decay to half of its value in 485 microseconds in this specific case. So firstly, on the left, you can see an isolated PV tracker or PV structure within the system that's connected to the grounding system on the sides. And we then strike lightning into the DC system or onto the PV module directly. And what we want to measure afterwards is the following. We want to see where this DC cable goes downstream and connects to a combiner box. So in a PV plant, typically all these strings, if it's a central inverter type PV plant, they have a lot of DC strings that are connected to a combiner box. And all these strings would go to this combiner box and only one string would feed back to the inverter system. So what we want to check is if lightning strikes into the DC system and makes its way to this combiner box, what would the current be on that earth bar or within that combiner box? This is typically where we would install the surge protection. Okay, so if you remember from the standards, we said that the surge resistor installed there only needs to handle between 10 and 20 kiloamps to be compliant. And that's according to most manufacturer standards as well. So it's not low, it's typical. So firstly, we will measure what happens at the DC combiner box. Then we want to measure what current is going through this bonding cable when it actually goes through to the pile into the grounding system. And then lastly, the DC modules or the PV modules actually have DC strings and DC cables underneath them. You can see here with the blue line and the green line. And when they are separated far apart, we will see that induced effect that we saw in the lab testing. And we want to see what current and what voltage is generated within these DC strings to see if that will also cause subsequent damage to the PV modules and whatever electronic equipment is installed inside that combiner box. So when we inject lighting onto the PV module, the first thing we see when looking at the combiner box, so SCB is a string combiner box, and we look at the earth bar where the surge resistor was installed. Now I said surge resistors installed there only need to handle between 10 and 20 kiloamps. What we can see immediately is that it's in excess of 50 kiloamps. The reason for this is that the lightning current doesn't find a sufficient way to jump across insulating material, and a lot of the current collects within the PV modules itself, and it would flash into the DC system, like the picture of damage that we showed you where the insulation was broken down. The lightning current will then make use of this DC system and go back to the string combiner box where you would see 50 kiloamps, and that actually would cause damage to that string combiner box and the surge resistor, and it would cause further damage downstream to the point where it ties into the inverter. So immediately we can see that it's not as simple as replacing a single module. There will be other subsequent damage further downstream that can cause you to switch off and isolate a specific block to do maintenance. So you will have loss of revenue and also loss of equipment in this case. So it's very important and very critical to understand that the surge resistors are rated much lower than what you would typically see within this lighting current that we're measuring on the string combiner box earth bar. Just to refresh and go back, so what we mean with what the standards say between 10 and 20 Ka, you would see for typical lightning level 3 strike, which is 100 Ka, we would only have to protect up to 10 Ka and 20 Ka to comply to the standards. But 50 Ka that we saw at the combiner box then exceeds these values, and it would definitely cause damage to the surge resistor and other further downstream equipment. Now, if we look at what current is going through that bonding cable or the bridging cable, the bridge across that plastic bearing, again, you can see that it's up to 25 kiloamps. Now, this is okay when you start using tested components that can actually carry this type of lightning current. Now, what the standards say in this case is that if you use something like a bridging cable or bonding cable as your down conductor system, the minimum dimensions is 25 millimeters square of copper up to 50 millimeters square of copper. So the 50 millimeters square copper cable would typically be if you have worry about mechanical stress on the cable. If you're not worried about mechanical stress, you can go down to 25 millimeters squared cable. So in the case where we did this study, we used a specific tested bridging cable. So this bridging cable was tested up to 50 Ka of direct lightning current, and we measured 25 Ka through that bridging cable, so it was fine in this case. In this case, none of those type of components were being overstressed. And then the last piece is the DC loops. So we spoke about DC loops underneath the PV modules. Okay, so we also spoke about the induced effect that we would see on these DC loops that can cause an overvoltage and current within the system. Here you can see the actual voltage that we measured on those DC loops and DC cables, and you can see that it's extremely high. It's in excess of 200 kilovolts. Okay, so the current in this case was really low, but the voltage was extremely high. And the PV modules at the back have these bypass diodes as part of the PV module's design. And if you look at the data sheet for a typical diode installed within these PV modules, you can see that its rating is around 30 volts. Okay, so this very high 200 kilovolt will also then cause damage to the bypass diodes at the back of the module. To protect against this, we typically want to make the DC look smaller, or we have to shield those cables by means of trunking or metal piping or anything like that to avoid this. Okay. Then we try to fix the problem, so we install air termination rods on the same PV plant, same setup. Only thing we add is the actual air termination rod, and then we inject the lightning current onto the air termination rod, and we then try to see what would happen again to the DC combiner box and the earth bar to see if the SPD would still be overstressed or we would still have subsequent damage further downstream. And then just for sanity check, also check how much current will now go through the bridging cable again, which is bonding the arm to the pile, because we now have a very dedicated path at this direct point. So firstly, what we see, the current immediately comes down from 50 kiloamps down to about 10 kiloamps. Okay, so the surge resistor in this case would not be overstressed. The reason for this is we have an air termination rod with a dedicated path of a lightning protection components down to the grounding system, which is attached to the grounding system. So as soon as lightning would strike the air termination rod, it would make its way into the grounding system, where it completely depends on the distribution through the grounding mesh. And by the time it reaches the combiner box, the value has been dissipated and it's much lower, and the surge resistor would not be overstressed. So this is textbook to what the standard says, why they want these air termination rods and these dedicated components and the grounding meshes. And it ties up perfectly with what we see we want to achieve with surge resistors and the electrical system. Then we look at the bridging cable again as a sanity check, and we see again that the value in this case is a little lower, but still obviously within limits. So it's at around 12 kiloamps to 16 kiloamps, somewhere around there. So the bridging cable that we used in this case, as you saw, was rated to 50 kA, so it will not be overstressed. Okay. So to conclude that, firstly, we want to make sure that we have dedicated lightning current paths, and this is to ensure adequate current distribution through the grounding system by the time it reaches electrical equipment. When it's attenuated, by the time it reaches the electrical equipment and surge resistors will not be overstressed. If we don't do this, further damage may occur downstream in the DC system past the point where the surge resistors were supposed to protect. And lastly, we want to keep the DC strings and the DC cable loops as small as possible to avoid any induced effects and any overvoltage that you would see as a consequence of nearby lightning strikes. Okay. In the second case study, we remove the grounding system component. So we have a PV plant with poor grounding, and we typically then want to see how the lightning current will distribute through the grounding network, and to see if equipment would be overstressed in other various places within the PV plant. So this is a typical setup of such a PV plant. So you have your PV modules, your DC component on the far right side. It goes through an inverter and it gets stepped up with a transformer into the grid towards the utility. Now in this specific case, this company had problems with their grounding fuse. Okay, so the DC system was connected to earth or to ground via a small grounding fuse, and this grounding fuse kept on blowing and damaging every time they had a thunderstorm within the facility. So when we looked into the ratings of the fuse itself, it's a very small fuse. So in this case, it's a 5 amp fuse with a breaking capacity of up to 50 amps, and it has a melting integral of 29. Okay, so The melting integral is something that I'll explain towards the end of the slides, but this is the key factor on what we try to calculate and measure using XGS Lab. Okay. Now, if you look at this again, this is the different PV plant now with the top view. It's made up of 3 different blocks in this case. Each block has its own inverters installed. Okay? And what you can see is there's no meshed grounding system in this case, but also they have an islanded system. So this top portion and this left portion is actually not connected via the grounding system to this main central portion. Okay, so the current distribution, we assume, would heavily distribute through the electrical network to make its way to the other parts of the islanded grounding system. Okay. Now, we investigate 3 different scenarios to make sure we cover all the different bases. Firstly, the most obvious one, we have a direct lightning strike within the PV plant. And then the second one is we look at the closest nearby strike. Okay, so this in this case was 6 meters away. If you go back to the picture where we calculate collection areas, we set 3 times the height, and we take that as a radius around the structure. In this case, the height was 2 meters. So within a 6-meter radius, we would have direct lightning strikes. Directly outside that is where the nearby strikes would start, and that's why we chose the value of 6 meters based on the collection area from the standard. And then lastly, we look away at the furthest point where we can have surge damage. So that's up to 500 meters away. We said from that calculation, you can see we strike lightning 500 meters away from the PV plant. When we do this, again, we want to measure what happens within the system. So we measure in a few different places. The first one is we measure at the inverter ring, the inverter grounding system where the fuse is connected to, which is the closest to the lightning strike. And then we also check at the other 2 inverter rings that are further away. And as we suspect that most current is flowing via the electrical system to get to islanded areas, we look at what's happening inside the electrical system cabling, and we measure that as well. So what we specifically want to look for when we measure this is a value known as the amp²second or the I²T value of the fuse. Now, I mentioned a few slides ago that the fuse in this case has a limit of 29 amp²seconds. Now, one of the characteristics of lightning current that we have to look at is the charge of lightning current. Okay, so the charge of lightning current Q is if we take the area under that 10 by 350 microsecond curve. Okay, you do this by doing an integral of that specific area under the curve. Now, charge as a characteristic of lightning is responsible for the energy conversion of the lightning strike at the point of strike. So ultimately, this is what causes melting and puncturing and things like that of the point where it strikes. Okay, so there's a lot of thermal energy involved, as you can see from these examples. Obviously, a fuse is something that will blow based on thermal energy going through the fuse as well. But a fuse actually uses the value quite differently. So in a fuse, as I mentioned, they use a value known as the I²T value or the amp²second value. And if you look at an extract from the lightning detection standard 61643-12, if we look at something like a 125 amp fuse, for example, it will allow an I²T value of 40,000 amp²seconds to go through the fuse, and it will also allow surge current 8 by 20 up to 40 kA. Okay, so even though the fuse is rated at 125 amps, it will still allow surge current up to 40 kiloamps to go through. So we can't purely just look at a current value or peak value that actually passes through the fuse to see if it's exceeded. We also need to look at the amp²second value. Now, luckily for XGS Lab, they have ways to get this value extracted from your simulation, and that's exactly what we did. So when we wanted to see if the fuses are getting damaged, the first hint was doing the charge or calculating the charge, but we had to characterize it in terms of fuse terms. So we worked over to the amp²second or the I²T value. Okay, so on the left, you can see, for example, what we measure in all these different places where we had the fuses installed, and we have our wave shape. If we just take the area under the curve or integrates the curve itself, we will get the charge. For fuses, we do a specific type of integration known as the dual integral, and then we get this value converted into amp squared seconds. And the fuse limit was 29 amp squared seconds in this case for the small 5 amp fuse, and that's what we did. We had to investigate to make sure that it's not being exceeded. Now, when we measured in different places across the plant, you can see firstly, this is an extract of the nearby strikes up to 6 meters away. You can see that the amp squared seconds values that we measured were mostly above the 29 amp squared second limit. Okay. The reason for this is poor grounding and poor grounding distribution. And that caused a lot of energy to flow to the grounding conductor around the inverter rings and the locations of where the fuses were installed. By implementing proper grounding, we then got the values down, as you can see at the bottom. So we just went back to what the standard says, and we started establishing those meshes again to make sure that we have perfect distribution and perfect current attenuation through the grounding system. By doing that, you can see already we got the values much, much lower with very high percentage improvements. And by doing that, the fuses were mainly then not overstressed, even at peak value lightning strikes. So XJS now with the new version 9.6 release actually gives you these values directly when you click on a specific conductor and you do the calculation, which is very smart and a very nice feature to have. So to conclude what we see from the lightning simulation on PV plants and why it's important to have proper lightning protection and proper grounding installed by means of simulation, you say the following. Lightning is very important, firstly, because PV plants or free field plants or utility scale plants have a very large collection area. Because they have a very large collection area, there's a very big chance of having a direct lightning strike, and it's a high direct lightning strike possibility. Secondly, one of the most crucial and most important parts of a lightning protection system in a PV plant is a meshed grounding system or some form of achieving current split. If we don't achieve current split, surge arresters and other equipment may be damaged, and you would have subsequent damage further downstream. It's not isolated to just replacing a module or single combiner box. A lot of damage can occur on the DC system further downstream. And then lastly, all components that you use within your lightning protection and grounding system has to consist of tested components. When we do these simulations, we have a direct reference value to compare that to. If you can't do that, you would have to test the equipment and make sure in some other form that cables, clamps, and things like that are not being overstressed. And this includes both the internal and the external lightning protection system. So what that means is the internal lightning protection system is your surge arresters and your electrical protection, and the external lightning protection system is protection against direct lightning strikes by means of physical components. It means that surge arresters also have to be tested, and you have to verify these values that you are simulating against what the capabilities of the surge arresters are. So thank you for joining once again, and I hope that this was very insightful. I hope that you can take something away from this and that you hopefully can do some of these simulations and verifications yourself in future. I hope that you maybe learn something new in terms of a lightning protection system and why we have the different components and what to look out for to make sure that you don't have subsequent damage to these large utility scale PV plants going forward. Thanks so much.
Thank you, Yvonne. That was great. I think we're going to spend a little bit of time, if Yvonne wants to answer some questions.
Yes, thanks so much, Ted. Yeah, firstly, thanks for everybody that joined. I see it was actually a lot of people that attended, so thank you for that. And then maybe to go through some of the questions. So there were quite a lot of questions that came through in the chat. I answered some of them, but some of them I kept aside because I think it's maybe valuable to everyone. The first question obviously was regarding the software XJS lab. People asked what module is being used. So For these specific lighting studies, we have to do it in the time domain. So the XGS module is called XGS-A time domain, or XGS-A TD module. So that's one of the big questions. And then we got a lot of questions regarding the use of lightning air termination rods in PV plants. There were a lot of questions regarding shading of the air termination rods, that they might cause shading to the modules around them, and also about using a tall mast rather than these short angled rods. So the first one, if we talk about the shading, there's a factor that we use which is 108, and you multiply that by the diameter of the air termination rod to get the distance that it has to be moved away from the modules to avoid a core shadow and possibly damage the module. So if you take something like these normal air termination rods that are 10 millimeters, if you multiply that by 108, it's 1.08 meters. So if it is moved 1.08 meters away from the surrounding modules, you should not have a core shadow that can damage the module. It does, however, slightly maybe still affect the yield of the modules themselves, but it's not that significant, and it hasn't really been a huge point of discussion for utility scale plants on projects that we've done before. Now, if you take that same calculation and you work with less masts but bigger, taller masts, obviously they are bigger, and you would have to move them further away to avoid the core shadow, and then your area of protection also becomes a bit of an issue to actually get 100% correct. So regarding the masts or the air termination rods themselves, they are perfectly fine to use, and they were designed and tested for PV systems specifically. Another question that we got was regarding soil resistivity, and how does this affect the performance of the earthing grid during lightning strikes. Yes, soil resistivity definitely does play a role. Definitely, yes. The standards don't make specific reference to that in that specific standard. However, in some hidden parts of the main lightning protection standard, they do talk about 400 ohm meters, but it shouldn't be a very big concern when you work with something as small as a 20 meter by 20 meter or 40 meter by 40 meter mesh. Also regarding that, another question we got was what material should be used and how deep should the grid be buried. So what the standard asks for copper conductor, it's 50 millimeters squared, so 50 millimeters squared. And you can also use galvanized steel material, but then it has to be 78 millimeters squared solid conductor, and it's all installed at a 0.5 meter depth, also for drying and freezing. If I can go through some of the other questions. Another one was, are the air termination rods used on one side of the tracking system or both sides? It's a really good question. For smaller plants, we used to, because of the cost, it's not that expensive, we used to give it on both sides of the tracker system, so it protects at all different angles as the tracker system moves. It does, however, become a little bit of a costly exercise when you move to these very large utility scale plants. So we would install them only on one side of the tracker, and then coordinate with the tracker system settings. So when a storm front actually starts moving in, they have a setting where they go into what they call a stow position, which is the best for the wind loading on the tracker system itself. And then we just make sure that when it's in stow position, it gives the ultimate or optimized protection that it is supposed to give. There's another question regarding what specific resistance was considered during the calculation. I'm not sure what resistance this is referring to. Maybe if you can reach out to us with an email, that's something that I would really be interested in understanding and answering as well. I'm not sure if it's the grid resistance itself or any of the components. Oh, I see. Okay, so it was about the soil. Again, in this specific case, those were two different PV plants that we showed. In both. The one was in South Africa, which has a very high soil resistivity usually, so it was in the area of about 800 ohm meters, if I remember correctly. And for the second case, it was a PV plant outside of South Africa, and the soil resistivity was also around 1,000 ohm meters or something like that, if I remember correctly. Typically, these plants are installed in very hot areas, very dry areas where the sun is in abundance. So in these dry areas, usually the soil resistivity is quite high. There are questions on the price of an air termination rod. Again, it's about the size that you need, so it's based heavily on the tracking system. But what I can tell you is that they're really not that expensive, and it's been well received by the market up until this point. There are people also that ask for a copy of the user manual of the software. You're more than welcome to go onto EasyPower's website and get in touch for the XGS Lab software. They'll be more than happy to share that with you as well. I think another important question. So a lot of people asked about the lightning strikes the air termination rod, it goes into ground, and that's great. But what happens with adjacent cables and electrical equipment and things like that? If we go back to the collection area calculation, you remember if lightning strikes at a specific point, it still induces a surge, okay? And that surge will still be induced in the electrical cables of the PV system, and it will still make its way to electrical equipment like string combiner boxes or inverters, and definitely also the bypass diodes at the back of the module. To counter this or to try and mitigate this risk, you definitely still need surge arresters. So a lightning protection system consists of two parts, as I mentioned at the end, internal and external lightning protection. The external lightning protection system with air termination rods and grounding only forms part of the actual lightning strike and the conduction and distribution through Earth. There's still a surge current, and that's mitigated by internal lightning protection, so you still need surge protection throughout the entire system for any lightning strikes that occur within the plants or anywhere within a 500-meter vicinity. If you want to protect the bypass diodes and things like that at the back of the module, it would be a really costly exercise to install a surge arrestor at the back of each module. So what people typically do is they shield the DC cable in terms of cable trays, metallic cable trunking, things like that, to build like a Faraday cage around the cable itself. And also the routing precaution. So not to create large loops with strings, you start to create a very big antenna basically for that picks up the induced surge currents. So for the surge, you still need surge arresters, and you still need to take care of cable routing and shielding of cables. That's really, really important to understand. There's another one. How do we maintain separation distance between the air termination rod and the PV and the down conductor in the whole system? So the concern is that lightning current will flash over from the air termination rod into the module. So according to IEC 62305, there's a separation distance calculation, and the ground level is basically moved from ground up to where the air terminal connects to the PV structure. That becomes your new ground level. And we install the air termination rod roughly around 100 millimeters, so 75 to 100 millimeters away from the module, to avoid lightning flashing into the module itself and to immediately enter the tracker structure, where it goes to the bridging cables and the grounding system and distributes through Earth. So there's another question. Does the software consider IEEE requirements as well? Yes. So the software covers most international standards. There's British standards, European standards, IEC standards, and IEEE standards for calculating limits and things like that for safety. But in terms of the data on which you're investigating, that is still up to the standard that you are using and the limits that you're using in your standard. And the software doesn't actually really. I think that's everything, Ted.
All right. Well, I appreciate it very much. I just wanted to thank Yvonne for his time and for everybody for attending. Also, there will be a recording of this video that'll be up on the EasyPower website, and everyone that registered will receive an email with a link to that as well. Anyway, I want to thank everybody for coming, and that'll be it, I think. Thanks, Yvonne.
Thanks, Ted. Thanks, Ivan.
All right, bye-bye.